Hello, my name is Gnewuch, and I would like to speak about optimal cubature rules on Haar wavelet spaces and on spaces with fractional smoothness. So this talk is based on joint work with Josef Dick, Lev Markazin and Winfried Zickel. As the title already suggests, it is divided into two parts, one part dealing with Haar wavelet spaces and one part dealing with spaces with fractional smoothness. So let's start with a part on Haar wavelet spaces. More precisely, we start by considering Haar wavelet spaces of univariate functions defined on the unit interval. We fix a base B and consider B basic Haar wavelets psi over the unit interval, given by the following expression. So what do? We subdivide the unit interval into B subintervals of length 1 over B. And then the basic Haar wavelet psi is given by the characteristic function of the ith subinterval of length 1 over B times the square root of B. And from this we subtract the characteristic function of the whole unit interval multiplied by the factor 1 over square root of B. So after that we get a whole bunch of wavelets by scaling our basic wavelets. So for this we pick a resolution J, right, that's a natural number, and a translation K, a corresponding translation. So K is a number, a natural number from 0 up to B to the power J minus 1 minus 1. And then we get the Haar wavelet psi J I K, which is given by this expression. So here you see in the argument the translation by K, and we use the resolution for this to scale the variable x. Right, and here in front we have some kind of normalizing factor. We complete now our family of Haar wavelets by adding the unit interval, which should be denoted by psi 0, 0, 0. The resulting family is now not an orthonormal base of the space of square integral functions on the unit interval, but it's actually a Parseval frame, which means it satisfies for each square integrable function f, we have the following representation where this sum on the right hand side of the representation is converging in L2. Or equivalently, the following statement is equivalent to this one, to the letter 1 here, to the representation. If we look at the square of the L2 norm of an arbitrary square integrable function, then it is given by the expression on the right hand side. So we take the Haar wavelet coefficients of this function f, takes the absolute value, takes the square of it, and we sum them up over all indices y, j, and k. So with these Haar wavelets, we can define a Haar wavelet space on the unit interval. So we pick some parameter which could be considered as a smoothness parameter, alpha, and we pick parameters p and q between 1 and infinity, and we define the corresponding Haar wavelet space to consist of all square integrable functions on the unit interval whose wavelet norm is finite. Now the wavelet norm of such a function is defined in the following way. The pth power of the wavelet norm is given by this expression here. So the outer sum, we look at the resolutions. The resolution appears here in the power of this factor. And for a fixed resolution J, we look at all the corresponding translations and at all indices I, which vary from 0 to b minus 1. We have a look at these Haar wavelet coefficients. We take the absolute value, the pth power, and sum them all up, multiply them with this factor, and then we take the sum over all resolutions. This can be easily extended into S dimensions. So now we have a look at the Haar wavelet space on the S-dimensional unit cube. We want to define again wavelet functions that are now S-variate Haar wavelet functions capital Psi J, I, K. Now here J and I and K are multi-indices, and such a wavelet is given as a S-fold tensor product of these univariate Haar wavelets that we already studied on the previous pages. So here JL, IL, and KL are the lth entries of the corresponding multi-indices J, I, and K. With the help of these of this family of Haar wavelets, we are able to define the S-dimensional Haar wavelet space for parameters alpha and P and Q. So this is the corresponding Haar wavelet space of S-variate functions. It consists of all functions f that are square integrable over the S-dimensional unit cube and whose wavelet norm is finite, and the wavelet norm is defined in this way. So this is the pth power of the wavelet norm. Again, similar as in the univariate case, we have such a sum. Now here we sum up over all capital J's that should correspond to the resolution. And here we have our resolution multi-indices. We look for a fixed capital J at all multi-indices whose sum up to J, right? So this should be the one norm, really the sum of all indices, of all entries here. And this should sum up to capital J. And for such a fixed multi-index J, resolution multi-index, we have a look at the corresponding translation multi-indices and the multi-indices I, where each entry could vary from 0 to b minus 1. And we look at these Haar wavelets, the Haar wavelet coefficients of f, take the absolute value and the pth power and sum them all up. Multiply them again with this factor here and sum over all capital J's from 0 to infinity. This is a wavelet norm for S-variate functions, and actually it turns out, as we will see later, this function space as equipped with this norm is actually the S-fold tensor product of our Haar wavelet space of univariate functions. So now, after we have defined our Haar wavelet spaces, we can have a look at Quasi-Monte Carlo integration over the S-dimensional unit cube. So let us have a look at some specific point sets, namely at TMS nets in base B. Here, capital N should denote the number of points of such an TMS net, and that is actually capital M is nothing but B to the power M. We can have a look at the corresponding QMC rule, Q index P, which is an equal weight cubature rule, and the integration knots are simply the points from our TMS net. We will use this QMC rule to approximate this S-variate integral, which is simply given by the expression on the right-hand side. So now what we were able to prove is, if we have a look at parameters P and Q between 1 and infinity, and a kind of smoothness parameter alpha, which is strictly larger than 1 over P, well, we want to have this condition because it actually ensures that point evaluation is well defined and is a continuous linear functional on our Haar wavelet space. If these two conditions are satisfied, then there exists a constant capital C such that for all m, for all natural numbers m, we have the following: the worst case error of integrating this integral is and approximating it with the help of our cubature rule QP over the Haar wavelet space. So this worst case error is actually defined as the supremum here on the right hand side. So we take the supremum over all errors of this form, where f is an element of the Haar wavelet space with norm less or equal than 1, right? So this is the definition of the worst case error, and we can bound this worst case error from above by the constant times n to the power minus alpha times the logarithm of n to the power s minus 1 divided by q prime. And q prime is the adjoint of q, which means nothing but 1 over q plus 1 over q prime is equal to 1. We were also able to prove a lower bound for the same set of parameters. There exists a constant small c such that for any cubature q that uses capital N integration points, the worst case error of approximating the integral with the help of this cubature over the wavelet space, over the Haar wavelet space, this here worst case error is bounded from below by c times n to the power minus alpha times the logarithm of capital N to the power s minus 1 divided by q prime. You see, these two bounds are actually matching. This means TMS nets achieves the best possible rate of convergence over our Haar wavelet spaces. There's maybe one thing which one should still point out. If you have a look at this factor here, you see actually if the dimension s increases, the convergence rate deteriorates. But that is only true if q is strictly larger than 1, because that means that q prime is actually some real number. In the case where q is equal to 1, q prime is equal to infinity, and this exponent vanishes, so is 0, which means that this whole factor vanishes, and we are left with the convergence rate n to the power minus alpha. So in the case where q is equal to 1, the convergence rate is simply n to the power minus alpha and does not deteriorate with as the dimension increases, which is really a nice property. Well, some of this results here for some sets of parameters were already known before. We should mention this. So, for example, in the case where p and q are both equal to 2, that is, in the Hilbert space setting, Heinrich, Hickanel, and Gnewuch, they proved a similar bound to our bound. It is really pretty similar. Instead of looking at cubatures that are induced by one single TMS net, they scramble this net, so they apply own scrambling to the net P, and this results in a randomized algorithm which gives you a Quasi-Monte Carlo cubature rule based on a random net P, right? Scrambling applied to a net, to a TMS net, gives you again a TMS net. And they were able to show that the worst case error, if you take the root mean square, so the average over the scrambling, then it satisfies the same upper bound than we saw on the previous slide. Our result is slightly stronger in the sense that we not only show that the average over all these quadratures, over the worst case error of all these quadratures or cubatures which appear here, satisfies this bound, but actually we show that this bound here on the right hand side holds for the worst case error of all resulting QMC cubatures, anyhow how the outcome of the scrambling is, right? So this is a little bit stronger. And in the case where P is equal to 2 is equal to Q, they were able to show the same lower bound as we did. Actually, our lower bound is motivated by their lower bound. We had a look at the proof approach, we modified it, and we were able to extend this lower bound to parameters P and Q different from 2. Right, in the case where P is equal to Q and both are equal to infinity, Enterer also was able to prove our upper bound for the worst case error of integration if you by using Quasi-Monte Carlo cubature rules based on nets. So he actually showed exactly our bound. He was not able to prove a general lower bound for the worst case error, which is matching this one here. So our lower bound now complements his result and shows, yeah, the upper bound he showed for cubature rules based on TMS nets is best possible, right? Okay, so now let's turn from Haar wavelet spaces to fractional spaces. Again, we start by looking first at the univariate situation. So we study first fractional spaces on the unit interval. We have a look at parameters p between between 1 and infinity, and parameters alpha, smoothness parameters, between 1 over p and 1. Now the fractional space, the corresponding fractional space, h alpha p, is defined in the following way. We look at all functions f which allow for the following representation. So there should exist an f tilde, which is an LP function on the unit interval, and some constant c, such that f of x is given by c plus the integral from 0 to 1. Now the integral over what? So first here we have this constant gamma of alpha, which is not very important. Then this function f tilde pops up here as some kind of density, and we integrate f tilde against this kernel here, against this kernel function. The plus should mean this function here is always 0 as far as in the case that t is strictly larger than x, right? So we have such a representation for any f that lies in this fractional space, and this fractional space was already studied before by Joseph Dick, and he showed that each function f in this fractional space is a Hölder continuous function with exponent alpha minus 1 over p, and in that case function evaluation makes sense, and f of 0 is simply this constant c, which appears here in this representation. Okay, so we have some interpretation of this constant c here. It's just this value. What about this density f tilde? Actually, it has some relation to fractional derivatives of order alpha in the sense of Riemann and Liouville, which are defined in the following way. So here we see this fractional derivative, and this is, apart from a constant, the following. First we take f and integrate it against this integration kernel, which is a little bit different than this one, as you see, and somehow this is, let's say, you gain in this way smoothness 1 minus alpha, roughly, right? And afterwards you take the classical derivative, that is, you lose smoothness of degree 1, and you are left with a gain of smoothness minus alpha, which is more or less a derivative of order alpha. So now the point is, this fractional derivative, if you compare it to the classical derivative is a local operator. If you apply it to a constant function, the constant function vanishes. This is not the case if you look at fractional derivatives, because they are integral differential operators and they're not local. That is why we have a look at a little bit modified differential operator. So before we take the fractional derivative in the sense of Riemann and Liouville, we first subtract the constant f evaluated in 0 from the function f, and we take the derivative afterwards. If f is a function from our fractional space, which satisfies this representation, then actually this differential operator, this function here, this exists almost everywhere, and it's equal to f tilde, which pops up here, right? So now we have an interpretation for this density f tilde. F tilde is nothing but this kind of fractional derivative of f, almost everywhere. Okay, so now Recall, if f is in our fractional Sobolev space and has this representation, f of 0 is equal to c, and the fractional derivative of f is equal to f tilde. Now we can define an anchored norm on this fractional space. So f should be, so the norm of f should be f evaluated in 0, you take the absolute value, the pth power, plus some constant times the p norm of the alpha derivative, the fractional derivative of f taken to the pth power. You sum both summands up, and afterwards you take the pth root of the result, right? And in the special case where alpha is equal to 1, there this fractional derivative is simply the usual classical derivative. Then this space, now alpha, sorry, h1p, equipped with this norm is nothing but the anchored LP Sobolev space of smoothness 1, so anchored in 0. So this looks maybe familiar to you, and this fractional spaces here with this norm, these are somehow generalizations of the anchored LP Sobolev space of smoothness 1. Good, now we can do the same, or we can generalize this to S dimensions. So we look at the fraction, we want to define fractional spaces on the S-varied unit cube. For this purpose, we look at the coordinate set from 1 to S, and we just use an abbreviation for this coordinate set. We consider parameters p between 1 and infinity, and alpha between 1 over p and 1. Now the fractional space of S-varied functions is defined in the following way. We have a look at all S-varied functions f defined on the S-dimensional unit cube, who allow for the following representation. So for each subset of the set of coordinates from 1 to S, there should exist some density f tilde sub u, which is an LP function over the unit cube in dimension size of u, size of the set u. And then f should satisfy this representation. So now what is capital phi of this family of densities? That is simply the sum over all subsets of the variables from 1 to S. Here you have some normalizing factor. Now then you take the integral over the unit cube of dimension size of u. You take your density function, integrated against the kernel, and this kernel is simply the product or tensor product of the univariate kernels we saw on the previous slide. And now here we have the kernels xj minus tj to the power alpha minus 1. And again, we have here the plus, so if tj is larger than xj, the whole factor here vanishes. And we take the product over all coordinates j in the set of coordinates u, right, and integrate. Okay, so this looks maybe a little bit complicated, but actually it's a straightforward generalization of the univariate space we saw before. Joseph Dick had a look at this, and he showed a few years ago that, again, if a function is in this fractional space of S-variate functions, then it's Hölder continuous with exponent alpha minus 1 over p, and if you evaluate f, then you get this f tilde, this density which corresponds to the empty set. Well, you only have to interpret now for u equal to the empty set, you have to interpret this and this integral in the right way, and then this comes out. Okay, now do we have an interpretation of these density functions here? Can we relate them somehow to fractional derivatives? Yes, we can. So f tilde of u is nothing but, now we have here partial fractional derivatives, so a product of partial fractional derivatives with respect to the variable xj and j runs through our set of coordinates. So actually this is a typo, this should be in and not equal to. So j should be in the set of coordinates u, and we apply it to, not directly to f as in the, so that we also did not do in the univariate case. We apply it to the uth component of the anchored decomposition of f. If you don't know what it is, well, you can calculate it by using and evaluating the function f in a number of points and taking alternating here signs in front and sum it all up. This kind of formula was shown by Francis Kuo, Ian Sloan, Greg Wojciechowski, and Henryk Wojciechowski in their paper from 2010 about function space decompositions. You can simply calculate the uth component of the anchored decomposition this way, and this here density is exactly this function, at least almost everywhere, right? This here is almost everywhere well defined, and it is almost everywhere equal to this density function. In this way, we could interpret these terms which appear here and here in our integrals as fractional derivatives, right? Okay, again, after this observation, we can equip our spaces of fractional smoothness of S-variate functions with a norm. It's just given by the sum over all subsets of coordinates of the coordinates from 1 to S. Again, here we have some normalizing factors. Then we take these densities f tilde sub u, take the LP norm and take the p's power, sum them all up, and the result, then we take the power 1 over p of the result, and that is actually our norm in our fractional space of smoothness alpha. Again, in the special case where alpha is equal to 1, this space equipped with this norm is nothing but the space H1SP, that is the anchored LP Sobolev space of dominated mixed smoothness 1, and this norm is the anchored norm on this set. Okay, so these are now the spaces which are of interest for us, and we want to do numerical integration on these spaces. So the question is, what are good cubature points for integration, for the integration problem on these spaces of fractional smoothness alpha of S-variate functions? The definition of these spaces is maybe not completely simple, and actually the fractional derivatives that are integral differential operators, that is a little bit more tricky to handle than usual classical derivatives. So maybe it's not good to approach this problem directly, or at least it could lead to a lot of technical problems. So our approach is now, we want to do function space embeddings. We want to embed these spaces of fractional smoothness into our Haar wavelet spaces, and we want to benefit from the optimal results that we already proved in the context of Haar wavelet spaces. We do the function space embedding via an embedding detour. So first we have a look at Bezoff spaces of smoothness alpha on the unit interval, so that are Bezoff spaces of univariate functions. And then we want to have a look at Bezoff spaces of dominated mixed smoothness alpha on the S-dimensional unit cube, and that will be denoted by this expression. Okay, now we have the following result. For the parameter p between 2 and infinity, and alpha between 1 over p and 1, we can actually embed the fractional space of univariate functions h alpha p into the Bezoff space of smoothness alpha and with indices p, p. And again, we can continuously embed this Bezoff space into the Haar wavelet space of, with parameters alpha, p, and p, right? Which we considered in the first part of the talk. This is nice, but this is somehow a univariate result. We want to lift it up to the S-variate situation. So for this, we need some kind of observation, namely actually all the spaces, all the S-variate spaces, or the spaces of S-variate functions we're interested in. So the spaces of fractional smoothness, this Bezoff space of dominated mixed smoothness, and this Haar wavelet space of S-variate functions, they are all tensor products of the corresponding spaces of univariate functions. And the good news is they are all tensor products with respect to the same uniform tensor norm, namely the so-called p-nuclear tensor norm alpha p. So this alpha p has nothing to do with this alpha, that's just a coincidence. So the p-nuclear tensor norm is called alpha p. And actually, so there's no relation between this alpha and this alpha. And yeah, so here one should say, if p is not equal to 2, we're not in the Hilbert space situation, right? So that means the tensor product is usually not unique. You can define different tensor products on Banach spaces, and actually we are in the lucky situation that all constructions here that we consider are of the same type, namely that are tensor products with respect to the p-nuclear tensor norm alpha p. That means, by elementary results from the theory of tensor product spaces, that our embedding results for the univariate case lift directly to the multivariate case, to the case where we consider S-variate functions. So our space of fractional smoothness of S-variate functions, H alpha SP, is continuously embedded into the Bezoff space of dominated mixed smoothness alpha. And this space is again continuously embedded into our Haar wavelet space of S-variate functions. Now we have an optimal result for here numerical integration on this space, and the upper bound, due to the continuous embeddings, the upper bound also holds in this space and also in that space, right? The only thing which may change is the constant. The constant may be changed, but the convergence rate stays the same. And that is what leads immediately to the next result. So let again P be a TMS net in base B, and let capital N be the number of points in this net. So our corollary is now the following. If P is a real number between 2 and infinity, and alpha is between 1 over P and 1, then there exists a constant capital C, such that for all natural numbers m, we have the following. The worst case error of integrating this integral with the help of the QMC cubature rule over the space of fractional smoothness of S-variate functions is bounded from above by c times n to the power minus alpha ln, the logarithm of capital N to the power s minus 1 divided by p prime. That was exactly the upper bound that we got in the Haar wavelet setting, and it transfers due to the embedding results directly to this setting of fractional smoothness. Okay, so we don't have such a nice result in the remaining setting where the parameter p is strictly between 1 and 2. So there it's a little bit worse, but still we are able to prove some reasonably good result. For every epsilon strictly larger than 0, there exists a constant c index epsilon strictly larger than 0, such that for all natural numbers m, we have the following. The worst case error is bounded from above by c epsilon times n to the power minus alpha minus epsilon. So that means the convergence rate of these Quasi-Monte Carlo cubatures, they have a convergence rate arbitrarily close to n to the power minus alpha, right? This is a little bit worse from the quantitative point of view, because such a result is obviously better, because here we see even how close the convergence rate is to alpha. This is made more quantitatively, but yeah, what to say? So at least we could see that the convergence rate n to the power minus alpha seems to be the right one for nets on spaces of fractional smoothness. These are probably the main results of our work, and I would like to close here my talk and point you to the two references here, the paper of Joseph Dick, and there the preprint, which appears hopefully soon, the preprint on which the talk is based. And yeah, I would like to thank you for your attention.